Hi gents, we're starting a new section on here. There's only 3 exercises in this section, so I'm only going to do one of the exercises. So we're doing reaction at supports. So basically, this is page 74. It says, for a beam to be in equilibrium, the supports must be able to withstand the forces placed on the beam. The addition of moments is used to determine the reactions at the support. So basically, it's saying here, if you have a look at these points here, A and B, they are the supports. So before in our last couple of sections, we haven't involved supports at all. So these supports have forces on them. And it depends on what the forces are on the top of the beam will determine the direction of these forces, okay? So let's have a little go. There's an example there on page 74 of how it works, okay? But let's have a little go. So exercise 1's on 74, you can have a go at that. I'm going to start exercise 2, which looks like this, okay? And it says here, find the reactions at the supports on the beams shown below. And I've done a little replica again. Okay, there we go. So it says we have our 2 supports, right? We got 2 forces, 60 newtons vertical, 100 newtons vertical, and 3 distances, 4 meters, 5 meters, 3 meters. So the first thing we should do when we do reactions at the supports is we know right now that there is some type of force on these beams, okay? We are presuming, I'm going to put this over here, we are presuming that if the arrow is going up, okay, so the arrow would be like that, going up, we should be getting a positive force. Okay, a positive force. If the arrow is going down, okay, so it'd be going back down, the same as that arrow there, you would be thinking a negative force. Okay. Now that's solely for these forces on your supports, right? So that's what you'd be thinking. We're going to name these supports because they don't have names right now. We're going to call this one RL, okay, and RR. So that just stands for RL is reaction left, because it's on the left-hand side, reaction right, because it's on the right-hand side, right? So let's have a little go. Let's try and work this out. So it doesn't matter which side you start from, okay? Now to add for consistency, I've always told my class to start from the left and work your way to the right, okay? So for consistency, we're going to keep doing that. So we want moments around RL, because that's where we want to start, right? Is equal to, okay, and we're going to say we're going to put this into equilibrium. So there's 3 forces right now. There's one there. There's a 60 newtons, 100 newtons, second force, and then this, RR, we know that's a force. We just don't know if it's a negative or positive force yet. So, we get our formula. So it would be force times distance plus force times distance plus, and we have one more, force times distance. Now that's equal to 0 because once we find out what RL and RR are worth, that beam will be placed into equilibrium. Okay? So let's have a little go. So if we had to put this in right now, we would have, okay, so our first force here. So we're starting here, remember. So this force here is pushing anti-clockwise, pushing clockwise. So it'd be a positive, so it'd be 60. From that RL, it's a distance of 4 meters, so you can put that in by 4 plus. The next force is 100, again pushing down, so it's clockwise, so 100. By the distance, 5 plus 4 is 9. And our final force is RR. Now we always presume it's positive, so we always presume that that force is pushing up. Okay, now we don't know yet, but we always presume it's going to be pushing up. So that's pushing up, so that's actually anti-clockwise. So we'd say negative RR multiplied by the distance, so 4 plus 5 plus 3 is 12. Okay, and we're going to say that's still equal to 0. So, that would be our formula right there, and that's our working. That negative RR is an issue, because we need to make sure it's a positive. So, I'll place this on the other side. So, RR times 12, now that's made it a positive. Now we can do these ones, so 60 times 4 is 240, plus 100 times 9 is 900. So there we go. Now we can go again. So the next part is we need to isolate RR. So we go RR multiplied by 12, okay, divide that by 12 so we can isolate RR. 240 plus 900 is 1140. We did it there, so we're going to do it here by 12. Now RR is isolated, so RR is actually worth, we work that out, so it's 95 newtons. It's a positive, so as we talked about before, positive force, it's a positive. So we place our arrow up. So right now we know it's a positive. So right now over here, you could place on your actual shape, you could say there's an arrow there, right? And it's actually 95 newtons pushing up. So we know that right now. So right now we need to find out what RL's worth. So, formula for that. We'll do it over here. So basically it's RL is equal to, and we want to find, and it's basically this. So, and I'll do this in green. So basically this is force 1. That's force 2, okay, and then we got our RR. So it's basically force 1 plus force 2 take RR, okay, so we can do that now. So that would give us, so force 1, as we know, is 60 newtons, okay, so you put that in, 60, plus force 2, which is 100, so put that in, 100. Take RR, we know that's 95, so you place that in, 95, okay. So RL is worth 60 plus 100, take 95, which is 65 newtons. It's a positive, okay, so we add our arrow in, positive, right. So that way up here on your chart again, you can go, there's an arrow there, okay. That is now worth 65 newtons. Alright, now you've just worked that out. So it said here, find the reactions at the supports on the beams shown below. You've found what RL's worth, it's worth 65 newtons. You've found what RR's worth, it's worth 95 newtons. Okay, good job, gents. Have a go at exercise 1 and 3. Okay, and we'll be moving on to the next section after that.